Hey, what's up, guys? Yeah. So the last time we talked about is crossing number inequality. So let me just first recall, right? So the idea is that given a graph G, so given a graph, oh, okay. So given a graph G, and the crossing number, right? Crossing number is defined to be the minimum crossing of the drawing of G. The crossing number is greater or equal to e to the cube divided by 60 v squared. So just small e is the number of vertices, a number of edges, and small v is the lowercase v. Okay, lowercase e is the number of edges, and the lowercase v is the number of vertices. So crossing number is greater or equal to e to the cube divided by 64 v squared if the number of edges is greater or equal to 4 times the number of vertices. Okay, so using this powerful tool, we can prove another famous results. Okay. Okay. So let me just give some the problem, right? So the problem we are trying to solve is this problem, right? Given a set of lines. So let me just a set of lines in R2 and a set of points that's restricted to distinct. Okay. Also distinct. So you just place a set of line in R2, a set of distinct point in R2. Let's call it set L. Let's call it set P. Okay. So then you can define the incidence. I should say the incidence. Okay. Okay. So incidence is defined to be IPL. So this set is defined to be the product of PL, such that so this P is in a point set P, and L is in a points in a line set, such that P lies in L. Okay. Probably hard to understand. So you can first give a two line. Maybe you draw two line, and let me just draw a point. Let's say I draw a point. Let's say this is my P1, this is my P2, this is my P3, and this is P4. Okay. So in this case, that my L is L1 and L2. My point P is P1, P2, P3, P4. And I can count this, right? I can count this PL, right? And this is trivial, right? So write down pair. So P1 is on L1, P1 is on L2, and the P2 is on L1, and the P3 is on L2, and the P4 nothing, right? So it's 4. Okay. Okay, so the natural question is that how large, right? So the natural question is how large can IPL be? IPL be, right? So you can place this, you can place a lot of lines, a lot of points, right? But the problem is that the 2 points can only determine line, right? So there's no, I mean, the obviously bound, right? The trivial bound is the following, right? IPL is bounded by the P times L. The number of point lines and times the number of lines, right? But this is too definitely should be smaller than it, right? Because each line can only 2 points can only 2 points can only determine one line, right? So if you have like a lot of points, there cannot be a way that each point lies in every point lies on all line. So this is the bound. This is a trivial bound that one can get, but one should be able to get the type bound compared to this P times L. Okay. So let me just give you the results. Okay, so this is the famous theorem that we are trying to prove in this video. Called Szemeredi Trotter. Okay, so this theorem is famous. I know this theorem very long time ago. Szemeredi Trotter theorem. Okay, so simply speaking, your IPL, right, is the big O. So or less or equal to 4 times. So at 4 is the actual bound. Okay, by P to the 3 divided by 2 divided by 3, 2/3, L 2/3 plus P plus L, and then this is just the same. right? So idea is that you can only get linear, you can get linear in points and linear in number of lines, but when you get the product term, this product can only bound by 2/3. Can at most is go to 2/3. Cannot be 1 and 1, right? So it's 2/3. Okay, I think the mysterious part is this one, is these two. Okay, so this 2/3 is hard. Okay, and let's get a feed. These two terms are trivial. So idea, for example, I mean, you can only take a one line, right? You can take one line and take all the points crossing the same point, crossing the same points. So in this case, that you're IPL, right? Let's say you have only 1 point, and you have L lines. Obviously, the instance is just L. Okay, so the linear term is not difficult. And you can also give a line and put all the point on it. Okay, then you will get an instance is basically proportional to the number of points. So this linear part are somehow trivial term, right? But the non-trivial part is this. The non-trivial part is this 2/3 term. So this is why the Szemeredi Trotter is the original proof is very difficult. But now one can use a crossing number inequality to get this down. Okay, and I also want to show that this bound is also tight. So we will see the example. Okay, so proof. So we want to start from crossing number inequality, right? So we want to say that the crossing of G is greater or equal to E cubed divided by 64 B squared, where E is number of edges, B is the number of vertices. Okay, so you have a lot of point and line, right? So you want to construct graph from your point line configuration. Okay, let me just draw something, right? So you have some points, right? This is a point, and let's say these are your line, and then you're going to, let's say I place some points here, right? So maybe P1 is here, P2, P3, P4. Okay, and let's say this is the point that I put. I try to maximize this P7, P8, P9. This is, so I try to maximize my instance, right? So this is why I draw this. Okay, so so number of the vertices, right? So to construct a graph, right? This is a planar graph, right? Or try to sorry, not planar graph. Okay, but the number of vertices should just be the number of points, right? So it's set P. Okay, so it should be but what's the edges, right? So edges is very simple, right? Given any line, the edges between the line between 2 points, the segment between 2 points, I define to be edges. So this is the edge 1, another edge, another edge. Okay, and for this one, this is another edge, and another edge. Okay, and this is another edge, another edge, and another edge, and edge. But basically, given any line, right? If you have all these points, then this I define to be the edges, the set of edges. Okay, so E to be da. Okay. Okay, now it's easy to see, easy to prove the results, right? So let's say the number of points is the same as number of vertices. What's the number of edges? Okay, so the number of edges defined to be this, right? But you have each line like that. You have some point set, right? So you can see that the number of edges. So for example, the number of edges is the same as the incidence, right? So the number of incidence minus 1, because now you can see that so let me check. If you have a line, right, you have 3 points. So the instance is 3, right? So the instance, so this line will contribution 3, but you only got 2 edges, right? So you should minus 1, okay? And then you total have number of L lines, right? So your total edges will be I minus L, okay? Right, because you have 3 points but 2 edges, right? So for each line you need to minus 1, and then you have L lines, right? So your total will be IPL minus L, okay? Now then, what's the maximum number of crossing? And this is trivial, right? Because the maximum number of crossings at most L squared, right? Because you have 2 lines, right? These 2 lines can only give you 1 cross. Okay, so you have L lines, right? You get L squared. Okay, so now we have L squared. crossing, right? Crossing is less or equal greater or equal to the IPL minus L cube divided by 64 V squared. Okay. P squared. Okay. So we get 4 P 2 divided by 3 L 2 divided by 3 plus L less or equal to IPL. Okay, I can times 4 here. Okay. So you can easily prove this, right? So when you write down, there's only L term here, but I can enlarge it to be times. I can just times 4 here. Okay, so this is the bound. Okay, and so you can see that this is the term that we try to prove. Right? This is the term we try to prove, but there I missed the P term, and the reason is the following: because in order to apply this, you will require that E greater than 4V, right? So in this case, what you're saying is that IPL need to greater than greater or equal to 4 times V, which is P. Okay, and so this is Q, right? So sorry, I'm still so you got IPL minus L. Your edges need to be, so in order to apply this, right? You need this. So if I don't apply this, that means that this is reverse, right? So in that case, your IPL minus L will less or equal to 4P. Okay, so it's L plus 4P. So I can just add P term here. Okay, so whenever I add P term here, then if E less than 4V, then this inequality holds. If E greater or equal to 4V, then this inequality also holds. Okay, so this finishes the proof. And okay, this finishes the proof. And let me just talk some results. So final thing I want to say is this bound is tight. So let me just go back. This bound is tight. And one example to see that is that you take P to be, let's say, n times n. So it's a lattice, right? So basically you're 1 to times n 1 to n, right? So basically it's just lattice 1 to n to n. We have some points, and then you can just take line to be y equals to mx plus b. So let's say, so the set of lines it's defined to be mb. Y equals to mx plus b, where m belongs to 1 to n, and b belongs to 1 to n squared. Okay. And then you can see that p and l is basically n cubed, right? Because sorry, this is n squared. Okay, so your number of points 1 is n cubed, right? L is n cubed. And you can see that probably a little bit hard to see, but one can try to compute the number of instants. Okay, it's basically n to the 4th. Okay, so you can see that this is the tight bound, right? Because your P and L go to 2/3. 2/3 is basically n4. Okay. So this finish is just tell you that the bound is tight. Okay, so this finished the proof of Szemeredi Trotter and using crossing lemma. So the next time we will see application of this on the so-called products sum product problem, which is interesting results. Okay, see you guys next videos.